Welcome to Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RDCCPS IISc. It's my pleasure to introduce today's speaker, Professor Debabrata Basu, and he will be speaking on when privacy meets partial information, privacy utility trade-offs in bandits. Debabrata Basu holds the INRIA starting faculty position in the school team of INRIA Center at Université de Lille and CNRS, France. He completed his PhD in computer science from National University of Singapore and École Normale Supérieure, Paris. Before arriving in Lille, he has been a postdoctoral researcher at Chalmers University of Technology, Sweden, and visitor researcher at Harvard University. His research interest is to develop algorithms and analysis leading to theoretically grounded responsible AI systems. Especially, he studies how to develop robust, private, fair, and explainable algorithms for online learning, bandits, and reinforcement learning problems. In 2022, ANR endowed the Young Researcher Award for his works on responsible AI. In 2024, he got elected as a scholar of European Learning and Intelligence Systems Society. His work on collective meritocracy in college admissions obtained best paper in the Student Presenter Award at ACM EMO 2022. In IGCAI 23, he presented a tutorial on auditing bias of machine learning algorithms, tools, and reviews. Audience is encouraged to ask questions at any point of the talk. For those attending online, questions may be asked either by unmuting or chatting directly in the chat box, from where they will be relayed to the speaker. Over to you, Professor.
Thank you. Thank you for the kind introduction. So already you know the title of the talk, so when privacy meets partial information, and I'll talk specifically about bandit problems and how privacy utility trade-offs are seen or studied in this topic. So how many of you know already bandits? Except you. Yeah, so okay. Quite a few. So okay, I hope for the first part you won't get bored much, but I would like to give a bit of idea or set up the terminology. Then we'll go to the data privacy part of bandits. So how many of you ever worked in differential privacy? One? Okay, so that part you won't get that bored. And then the step 2 is quantifying the hardness of differentially private bandits and what are the nuances in there. So we'll try to derive lower bounds as we know in bandits. And finally designing near optimal algorithms for differentially private bandits, and then we'll end with what we have learned and what we have not learned, basically what we can still work on. Okay, so the first part is about a short tour of bandits. It is about learning to take decisions when we don't have a complete information about an environment, and we acquire this information sequentially. So you know this classic example that everyone overfits on is the clinical trials in bandits. So if you are a doctor and you have this K number of medicines, and this is a magic medicine, if you put it, someone get cured or someone won't get cured ever, and the probability of getting cured is given to you. So which one you will choose? If you just look at the slide, which is the natural one? The second one, right? So that's pretty easy. But now let's say you don't know them, right? You don't know the probability of getting cured. So what you can do, you run a clinical trial. We have gone through COVID, we have seen things happening around like this. So what happens that at any moment of time, a patient comes in, the doctor pi, which is a algorithm policy, however you call it, chooses a medicine 80 among 1 to k. It observes the response, that is whether the patient is getting cured or not, and then it is going to use this history of choices of the medicines and the responses collected to decide which medicine to choose the next. And the goal is to maximize the total number of patients cured if there are capital T number of patients occurred in there, right? So now what is the performance measure in there? So as we said, maximizing the total number of patients that is getting cured, what we call in bandits often the reward. So we want to maximize the cumulative reward. But it is a random variable, so working with it is a bit like nuanced. So what we try to do, obviously we try to work with the expectation of it. So you want to maximize the expected cumulative reward, where the expectation is taken over all possible randomness of the environment itself. Then what is this called? If you have ever done reinforcement learning, this is often called the value of the policy. And Then this is the problem that people have started to study in 1933. So if you see the history, it started in 1933 with this kind of motivation of doing clinical trials. But whatever we are going to do, or however we are going to express, that comes from this paper of Robbins in 1952 onwards. And there comes this interesting change of concept. So for a long time, people are trying to maximize the expected cumulative reward. And that was the time of control theory rather than machine learning. And people were taking lots of control theoretic approaches in there. Even Bellman and lots of other people have studied this problem. Interestingly, it was known to be so hard of a problem that, at some point, I think Whittle, who devised the Whittle's index, he said like, so when during Second World War, Allied scientists were working on that, they said, okay, let's give this to German, probably, they'll stop doing scientific progress anymore. So that was the hardness of the problem, but then Robbins came up with this nice idea. He understood the main problem here is the partial information. So why not try to quantify just the cost of partial information? And that's why we come to the expected regret. Let's say you know the best medicine in the hindsight, you always use it, and this is the expected reward of it, right? So expected reward of the medicine A star applied T times. And your algorithm incurs the V by T, right? So this is the difference of the value of the optimal algorithm that knows everything in hindsight and the value of the algorithm pi that has incomplete information. And now the whole next 50, 60 years of literature became how to minimize regret. And that's still the paradigm we are in. And probably lots of you who have worked on bandits already know that minimum regret achievable is often quantified using a lower bound. And how we do that? We kind of write this expression. Again, the one of you like who know already, like don't get bored. This tries to say that basically there's this gap of distinguishing any arm with respect to the optimal arm. And KL divergence is the natural information theoretic quantity that says how a distribution is different from other. So we are trying to distinguish this PA from PA star. So we are paying inverse of that as our cost. And then mu star minus mu A is the expected reward that we are losing while trying to play them. And then there came this, okay, I missed the citation, but there came this famous bound of Lie and Robbins that said that we have to do for the suboptimal arms, so the arms which are not A star, this log divided by KL number of times. We have to pull them this many times to understand that they are suboptimal. And if you want to get an intuition who are not very banditish people or not used to it that, you can think of this for Gaussians. This is roughly like the variance of the arm divided by the difference of mean of that arm from the optimal arm. So this is often called the suboptimality gap, and this is obviously variance. So this inverse of variance is kind of one important intuition that people try to play along for the next few decades, and that gave us kind of the optimal algorithms with Euler and other the famous ECV type of algorithm. The whole idea was, okay, if this is the gap that we want to dwell on, then probably we want to sample arms in the inverse proportion of it. And how we can do that gave us all the optimistic algorithm in some sense. And then the other one, so today we are not going to do regret minimization, so we'll just take it as one of the utilities that we can play in Bandit. Then the other utility that got pretty famous in last, let's say 20 years, specifically last 15 years, let's say, is this base term identification problem. So then people said, if I am really trying to do the clinical trial, probably I want to interact with as less number of patients as possible and identify which medicine is the best one. So what I'm trying to do, I'm trying to find out the arm that has highest mean or highest probability of getting cured, right? Curing any patient. And what I want to do, I want to stop the interaction at some time tau and recommend an arm A hat, which is with high probability the best arm or the arm A star. And what is the utility in there? So if we want to devise a 1 minus delta correct, which often we remove the 1 minus delta and call it delta correct, algorithm are the set of algorithm where if you give any family of instances from this class M, any bandit instance from there, it stops at a finite time and with high probability, probability greater than 1 minus delta, gives you or recommends you the optimal arm. Okay. So in that case also, our goal or the utility is to minimize this stopping time while staying accurate. And here also we know the minimum expected stopping time is lower bounded by something called a characteristic time times log of 1 by delta. This delta is the probability of error that you anyway consume, right? So this inverse of this is again dependent on expression of KL divergence between the arm that you are playing and the mean of the arms of the alternative instances. Why I am trying to emphasize that? It shows that whether you are going through the regret minimization problem or the base term identification problem, both cases KL, and if you see, this is the inverse of a version of KL that dictates how hard the problem is, because the cost of partial information is incurred through the KL divergence, where you are trying to distinguish the environment you are actually playing and the possible environment that you can say like that is an alternative, right? That you can confuse it with. So often we call it also confusing instances. So this, if we look into this, then we have two types of utility objects that we typically study in multi-arm bandits. One is minimizing the regret given an environment mu, a number of interaction capital T, and then the other one is the fixed confidence based arm identification, where we want to minimize the expected number of interaction given an environment mu, and we want to still recommend with 1 minus delta probability the correct based arm. And the information theoretic crux here is we always want to control the KL divergence between this true instance mu and another instance lambda, which we might confuse it with under this incomplete information scenario, right? So this is what, out of all these slides you have seen, I want you to remember that there are two types of utility objectives. The information is gathered sequentially, and this number of interactions that you need or number of the utility loss you face really depends on this quantity, that is the KL of the instance and an alternating instance. What is an alternating instance? Where you might have a different optimal arm. Everything looks same, but the optimal arm is a bit different. So this is the alternating instance you are trying to distinguish from. So now, once we understood like what is bandit and what we are going to talk about and what is the main information theoretic quantity that we are going to deal with, we are trying to now define privacy in bandits. So here comes the first challenge, or like let's introduce the classic definition and then we'll go to the challenge, is that how to define data privacy, right? So there has been a long set of definitions, conflicts, like what is a good definition of data privacy, and in the end we found out that the differential privacy came up as the gold standard to save data privacy in machine learning algorithms because of their statistical nature, and it kind of molded into the statistical structure very easily and finely. So what is the idea of it? The idea of it is that when an analyst accesses a database or puts a query or runs a machine learning algorithm on a database where you have your data and where you don't have your data. So this is the case, you don't have your data, database 1, and then I add your data and I have database 2. In both cases, after you're running your algorithm, you get result 1 and result 2. If the results or the outcomes look almost similar with respect to both the databases, then anyone who sees the outcome, basically the user, cannot distinguish whether your data is in there or not. So basically, if we go for the mathematical formulation, we want to say that if you run an algorithm pi on a database where you have your data and get an output O, and then another database where you don't have your data, you run the algorithm and get an output O, the probability that this event happens differs only by e to the power. And if we be rigorous, then this is upper and lower bounded by e to the power epsilon and e to the power minus epsilon. Okay, so because this is a commutative definition, you could put the ratio in the other way also. Okay. So are we clear about this intuition? Because this one is kind of crucial. Lots of you knew bandit already, but for the differential privacy part, are we good with the definition? You see why like we want to do it, right? Because rather than removing your data completely, you want to say like what matters is someone else rather than the analyst or the algorithm should not be able to identify your data or any property of it. And you are trying to statistically ensure that. Okay. So this is often called the epsilon differential privacy. The epsilon is called the privacy budget. So as you can see, if epsilon goes down, this difference goes down. So epsilon can go up to 0, then this ratio is 1 and you cannot distinguish anything. If epsilon goes to infinity, this ratio is completely distinguishable. So this is completely non-private scenario or the usual one you face. Okay, so lower epsilon is better. Just let us remember that. Okay. Okay. So now if we see in this one, yeah, oh, please.
Pi of dB means the policy has been learned using the dB only, right?
Yes.
And pi of dB plus my data is policy is being learned
With the database plus my, yeah. Okay. Any other question? Okay, cool. So now, if we look into, okay, let's not go into the next slide. Let's look into this. So if we kind of dissect this definition, what are the important components in here? So I have to define my input space, I have to define my output space, and I have to be able to define a measure on the outcomes of my algorithm, right? And in here, there's an important result that no deterministic algorithm applied on a data can achieve differential privacy. It has to be a randomized algorithm, okay? So that's why often what we do is, like, if there's a deterministic algorithm or a statistics calculation underneath, we add a noise to that so that it looks randomized, and then we define privacy on this noisy statistics or noisy outcome, okay? So the first question we faced, and everyone back in time was encountering when trying to define differential privacy for reinforcement learning or the sequential incomplete information scenarios, is what is the input, what is the output, and how to properly define differential privacy in there. So first we, in this 2019 paper, back in my postdoc, when we got interested in this problem, we are trying to understand the graphical model of generating data in multi-arm bandits. So let us consider this new is the environment, that is the bunch of probability distributions that we are interacting with. So if it is not in white, that means it is latent. Then at any point of time, there's an algorithm. Again, this algorithm might be latent, you cannot see all the inherent parameters of it, but what you observe is the choice of medicine by the algorithm that generates a reward. Then this reward and the previous action is used to take the next action, and then it again generates a reward. So what we can think of that if this is kind of an infinite tape of input and output going on, the set of observed responses, that tape is basically, or set of rewards is basically your input, and the output is the set of decisions. And what is data privacy in there? That if we think that at any point of time one patient is coming up, you want to, and the patient might want to keep her response private, right? So basically we want to obfuscate or we want to blur this RT while this AT is public. Because in a clinical trial, you have to tell what are the medicines you have applied to people, how many of them, but you don't have to tell whose response was what exactly, because that might leak their private medical situations, right? So which is confidential. But then there came like two types of models. So if you have seen differential privacy literature, often we call there's local, and here we called it global, but it is often also called centralized models of differential privacy. What is this model? That at any point of time, if you generate a medical response, you might trust the doctor, you might not trust the doctor. If you trust the doctor, then you send the true reward to the algorithm, and then the algorithm tries to take decisions in a way so that the decisions don't reveal your rewards or responses. But in the case you don't trust the doctor, you already add some amount of noise to your reward and then send it to the doctor, and the doctor takes decision accordingly. This case where the user itself adds noise to its response is called local DP. And if the true reward is sent to the algorithm and then the algorithm does something to obfuscate this information, then it is called global or centralized differential privacy. So if we try to formally define the global one, then the probability that the set of decisions given the possibly observed responses of this capital T number of patients plus my data, whoever is asking their data to be obfuscated, and then the probability that the set of decisions are the same given the possibly observed responses of T patients don't include my data, would differ by maximum e to the power epsilon. And in this case, I don't go up to decisions already. I say what the observed response is for the algorithm given the actually generated responses, and where it includes my data and where it does not, should not differ more than e to the power epsilon. So in this case, we'll try to focus mostly on this because this case is much simpler statistically and information theoretically, though in practice it is very important. Yeah. Also, when we are saying capital T number of patients, we are trying to mean that there are capital T number of maximum interactions we are considering. But this T can be any arbitrary natural number. So, yes. So a single algorithm running at this point.
And so who are, I mean, I thought it was a, in your mind, what is my data? Who's me?
Oh, so basically a patient small t, like who comes up at the...
Each time slotted thing is a patient.
Exactly, yeah.
And
yeah.
then you get to observe certain time slots plus one time slot which is not revealed.
Exactly, So any other question? Yeah, because this definition has to be like clarified. Yeah, it's good. Okay, so then this local DP one is pretty useful in practice because this idea actually came up long ago when people were doing social surveys. And the first local DP algorithm, though there was no DP back in time, came in 60s basically. And it was a social scientist who said like, you have a right to plausibly deny rather than saying exactly your preference if the survey is sensitive. And that is the plausibility denial, right? So you are not giving your opinion or your medical response directly, you are adding some noise or flipping it with some probability. So it is very useful in practice, and often this is deployed. For example, if you are using the Apple keyboard for auto, like for predicting your next word, then actually that uses local DP in there. But in this case, to have the mathematical fun, we are going to look into global DP mostly, but the local DP is also studied and well understood in this case. So now the next question that we came up with, that okay, for lots of time, so as you can see, like when we started is roughly 2019, and before that there are papers since like I think 2016, all of them were studying this global DP and local DP in some sense. Local DP was roughly resolved, we have the lower upper bound in this paper, but then this was not resolved, and every time people are coming up with a new definition. So till 2023, 2024, we are in a kind of dilemma. What is a good definition for global differential privacy in bandits? So the most popular definition that has been used called the ViewDP. What is the ViewDP? It says that if I run the bandit algorithm, I get a tape of rewards, right? Capital T number of rewards, and then I can get another tape of capital T number of rewards, which differs at one place. So if let's say the second patient said, I want to obfuscate my data, you get R2 prime rather than R2. So these are often in differential privacy terms called the neighboring data sets. So the neighboring data sets are defined as the two reward tapes. The rewards, those are observed, and then your distribution of outcome is the distribution over the action sequences given the realized rewards, the rewards really observed over. And this is the output you are getting. And what is the ViewDP? That if you have used a reward sequence R versus a reward sequence R prime, the getting the same action sequence differs in by a slack e to the power epsilon. Okay. Though this seems like a very natural definition, there has been multiple problems, because why? The environments in bandits are themselves stochastic. This reward sequence you are seeing at this point of time might not be the reward sequence you are going to see in the next point of time. You run the algorithm. So if you want this stochastic nature to be taken care of, you should not work with this, because you can show that this definition might leak information if you run the same private bandit algorithm multiple times. So what we instead studied around 2023, 2024, because our initial works were also stuck in this paradigm, we saw that actually we should define it like this, that let us consider that all the medicines, if they have been applied on all the patients, then it would have generated this underlying table of rewards. And now if a patient says, I want to obfuscate my data, that means I want to remove a whole row from this table. So what we are saying, that we are saying these tapes are stochastic. These tapes are dependent on the actions I am choosing. So to remove that stochasticity, I am defining the database as all possible generated rewards that is underlying somewhere. I don't see them, doesn't matter, but that is my true database. And if I can define now the action set, so these as input and the actions generated over time as the output, then that is the case, like this D and D prime, they differ in one complete row, and I want to generate the same set of actions from these both cases where they differ in probability by e to the power epsilon. This is the table DP, and why this is a good definition. If you want to ask for the intuition, if you run your algorithm, which is stochastic itself, if your environment, which is stochastic itself, goes through this and you see any of the trajectories after running the algorithm, they're all private at the same time. Okay. And that is very important in this interactive setup, because if you think of an adversary, in this setup the adversary can be interactive. It can give you a different reward at every point of time. If you think that between the person you are interacting with and the action you are taking, there is someone who is obfuscating the information, they can adapt with time also. So there can be an adaptive adversary really, which was not there in the classic differential privacy in supervised learning setup. And you can show if you satisfy this definition against any deterministic adversary, you can satisfy differential privacy against any adapting adversary. So this is the definition that we should go for, and we started going after 2023. So we wanted to obviously give more reasons why to study this table DP. Is first that table DP and view DP, they're implied by, so there is, oh yeah, right. So yeah, okay, that's fine. Yeah, so if we want to satisfy only pure differential privacy, which we have talked about right now, then table DP and view DP are equivalent. And most of the people in the bandit literature actually studied only pure differential privacy. So for them, there was no problem. So the things were true and correct, but then there is a relaxation of the epsilon differential privacy. What is that? You say that, okay, this is too hard of a constraint for my distribution. What I want to do is rather satisfy this ratio plus a delta slack. So which is often called the epsilon delta differential privacy or approximate differential privacy. And if you introduce this slack, you start to see that epsilon delta table DP satisfies epsilon delta view DP, no problem. But if you want to satisfy now epsilon delta view DP, it gives you epsilon k to the power t delta table DP, and which is like an exponential blow in delta. So basically, roughly, if you have a slack of k to the power t delta in here, which says like your differential privacy does not make sense anymore, right? So in practice, you want to use table DP, and you can strictly show that the table DP policies are kind of a superset of this view DP policy set. You can really create a counter example and show it. So this is the reason we started working on table DP, and that is kind of now considered as the standard way of doing it. And at the same time, people working in differential privacy, they have a term called differential privacy under continual observation. So came up with this similar definition, and that has become the standard in continual interactive settings. But one thing I would like you to remember, unlike the utility objectives that we have seen, privacy is a worst case guarantee. The utilities in bandits are all stochastic, their expectations or like high probability guarantees. But privacy is a worst case guarantee, and the table DP allows us to satisfy it against the worst case adversary and for any randomized algorithm. Okay, so now our new problem is differentially private multi-arm bandits, where we want to achieve both privacy and utility. So we want to design an epsilon differentially private policy that minimizes the regret, or we also want to minimize the expected number of interactions to design a 1 minus delta correct and also epsilon differentially private policy. But now the question comes up, what to control in here between the instance you have seen and the alternative you can confuse with when you have incomplete information and also epsilon differential privacy. Yeah.
So you are considering pure differential privacy still?
Yes, for most of the exposition here, it is pure. Yeah. Here, no. Like if we want to go for lower bounds, it does not matter. But this is for ease of exposition only. But all the lower bounds we see can be extended to approximate cases basically. Yeah. Okay. So, any other question? Okay. So now we move to the third part of the talk, where the main technical contributions come in. So now we know what are the utilities we want to achieve. We know what is a good definition of differential privacy. Now we want to understand what is the information theoretic bottleneck that we want to work on to understand differential privacy in bandits, right? So first, high level overview of it. If we summarize all these results in a more understandable fashion, we see that the lower bounds for the minimax regret. So there are two types of regret lower bounds that we minimax one is the problem dependent one, and this is roughly like square root of k. K is the number of arm and t is the number of interactions. In case of epsilon differential privacy or the global differential privacy, it is the maximum of square root of kt and k divided by epsilon. Okay, so that says that if epsilon is less than 1 divided by square root of t, roughly, I am not considering the k part, then only the privacy becomes the dominating term. The privacy becomes the dominating term in the regret. Otherwise, the cost of partial information is always higher than the cost of privacy. And then for local differential privacy, we see that there's no sweet trade-off like this. We have to pay straight by a multiplicative factor of 1 divided by epsilon. And as we remember, going low epsilon is our goal for privacy. So we increase the privacy, the regret increases, right? And in this case, for problem dependent regret, we have seen KL as the core term that actually dictates how our regret will change. And in this case, if we see the simplified term, we see that the suboptimality gap appears here, so sigma square divided by suboptimality. But here, this is sigma divided by epsilon that appears directly. So if and only if your epsilon goes below your suboptimality gap divided by the variance, then you start to pay the cost of privacy. Otherwise, the cost of partial information is always more. And for local DP, you see a straight factor of 1 divided by epsilon square coming up. So if you want to satisfy local DP, always achieving more privacy has to incur more regret. Okay, there's no sweet trade-off in there. And this matches the intuition. Basically, for local DP, we are adding more noise. We are adding noise to the each and every response. In global DP, we are aggregating the true response and then adding noise. And in non-private, we are not adding noise at all. So as the amount of noise injected decreases, the minimum achievable regret goes down and down. And that also says that there are two regimes of differential privacy, as we have discussed. So now let's go a bit more involved. We try to understand why this is appearing and how to prove the lower bounds in bandits. So if we see here, the key observation for proving a lower bound in bandit is understanding how to distinguish the true bandit environment. K distribution, the K reward distribution, another bandit environment, which is almost similar but the optimal arm is different. You have an opportunity to go through a sequence of capital T number of rewards, sample this arm and this selected or sampled from a. So basically, you are doing a multiple hypothesis testing at the same time. You are trying to identify the arm that has the highest mean while comparing it with all other possible arms, right? And then the whole point comes up or boils down to what is the bottleneck of doing a sequential hypothesis test. And the bottleneck of doing a sequential hypothesis test depends on, so let's forget this term, depends on this thing, which is basically the distribution induced by the true environment after capital T number of interactions and using the policy pi, and then another confusing distribution mu prime using the policy pi, and again after doing capital T number of interaction. If these two distributions, their KL divergence is high enough, you can distinguish two environments, you can do a hypothesis testing. If they are very close, it is very hard to distinguish them. Okay. So now if this is the quantity that we know from the hypothesis testing literature and classical bandits that dictates our lower bounds, the question is what happens, what changes under epsilon differential privacy, right? And this is the thing, that's why if you go to the fixed confidence BI, if you go to regret, the KL always pops up, because this is the quantity that actually dictates the sequential hypothesis test. Now the question we asked, what changes in there if we start to apply epsilon differential privacy? And the main thing that changes, that if now we consider pi epsilon, which is a epsilon differentially private policy, then we can upper bound this scale with this term. What is this? This is epsilon times the expected total variation distance between the arm I have selected from the true environment and the arm that I have selected that could have been in this confusing environment. So what is this? This is saying that if you are used to it, the bandit or the sequential hypothesis testing proofs, this says that this scale can be decomposed directly over time. So that is an equality. Here we are saying, no, you cannot do that anymore. Rather, you have to use an upper bound that gives rise to a total variation distance between the arm you are pulling in the true environment and the arm you are pulling that could have been in the confusing environment. And this makes a big shift. What we start to see is a new type of lower bound in bandits. So we know in bandits like different types of KL divergences appears, different types of alternating instance we have to consider. And again, for more pro-bandit people, this is often called the KL inf that actually dictates the lower bound and how much we can be efficient. But here we start to see a new quantity or a new divergence appearing that is called the TV inf. So what we are trying to do, we are trying to identify that how the PA and another P prime are different, where the P prime can have higher mean than the optimal arm. So basically it has a different optimal arm than the true environment I am working on. This TV inf really dictates how hard is your problem. And this makes it super interesting. So we see like whatever existed around 2018 for Bernoulli bandits, there we see that this total variation distance becomes actually the suboptimality gap. So these suboptimality gaps cancel and we get the 1 divided by epsilon bound that we have seen in the first simplified slide. And then if we just keep them alive, then we start to see if epsilon is greater than the KL divided by the total variation, then the privacy can be achieved for free completely. And if it is less than that, then the privacy, you have to pay for privacy. And this was a very, very interesting result that actually made me very happy, because when we started studying it around 2018-19, the folklore was like reinforcement learning, achieving privacy in reinforcement learning is going to be very costly, because you don't see the data. You have to keep on adding noise so that any future event is obfuscated, any future addition is obfuscated. So you have no other way to minimize this noise addition. So roughly like whatever we have seen there, like this 1 by epsilon factor, that was the rough expectation back in time, that there will be a multiplicative factor and you cannot avoid it. But now we see a sweet spot that in most of the cases, actually you never pay for privacy, because the cost of partial information is so high information theory. And then we see the similar phenomena appearing in the base term identification. So as you have seen, this was the KL divergence before, but now you start to see that there's total variation that appears and you get a TV characteristic time rather than a KL characteristic time, and the 1 by epsilon factor appears naturally. Okay, so now you have two environments, two regimes of hardness. So basically if you see the epsilon is greater than this T star TV divided by T star KL, privacy can be achieved for free, and otherwise you have to pay for privacy. But this is typically the scenario that people use in practice, in industry. It's very rare that any cases in practice people use this type of epsilon. This is cool for us theorists, very nice to study, very fun regime. This is very bland, but in practice this is where we stay always. And if we want to understand this simply, we see that the KL is roughly 1 divided by delta square and the TV is roughly 1 divided by delta. So basically if your epsilon is less than 1 divided, epsilon is greater than delta, so you don't pay anything, and roughly delta is very small, right? So you almost always satisfy that. Okay, so now we saw our lower bound, we saw a new type of TV in appearing, and the question that next comes up naturally is how to design algorithm. But before going into that, any question, anything? Yes. Yeah. Sure, yeah. So that's the part I can discuss a bit in details. Maybe I'll use the board for this. So this is, I think, more visible to everyone. So, okay, from where does it come, right? Okay, so let's start with the definition of privacy. So what we said, that there's a database D, right? That is the bunch of reward generated from the K arms, and then over time T, right? And then I change this one of the rows and I get another database called D prime, right? Fine. So now what we know from the definition of differential privacy, that if I apply a mechanism M on this data D, and if I apply the same mechanism on this neighboring data set D prime, and I want to look into any event E under this and also under this, their probabilities differ by a factor e to the power epsilon, right? So now what does this mean? The KL between this MD and MD prime differ maximum by epsilon. But this is written under the assumption that there is only one shift between them. But since we cannot control this shift, what we try to do, we try to define the Hamming distance between this D and D prime, and here we start appearing Hamming distance between D and D prime, right? Now this is a deterministic case, right, where this D and D prime are given to you, but you are studying stochastic bandits. So what happens, this D and D prime come from true distributions. And what are the distributions of your interest? That is, let's say one is this mu and another one is, let's say, lambda, okay? So this is the true instance, this is the confusing instance. And what you want to understand now, what is the KL divergence if these two things are generated from mu and lambda themselves, right? So what you can say now, that this thing, so under stochastic case, this thing. So if D was generated by interaction with mu and giving rise to D after T interaction, and then again lambda T after, okay, so that would be less than epsilon time the expectation of this D ham D and D prime, where D and D prime are generated from a coupling over mu and lambda. And what is this coupling? Since this is true for any coupling, you want to take the inv over it, right? We agree? Is this clear? Exactly, exactly. Because these two are not like separate generations, right? They are generated through the same interactive sequence. So you cannot make them independent. You have to define a coupling in there. And the cool property of this is that this is equal to the total variation distance between. Okay. And if you use this property and then use it, so this is the sketch, this is the main idea of it, but then you have to use it on the product distribution of the interaction, and then the product distribution can be decomposed further, so you get this sum out of it. Okay.
In the like lower bounds, you get a KL divergence on the right as well.
So in the usual lower bound, you get something like, so basically the right hand side looks like summation over KL. Yeah, so if I say, okay, I should not have used P, so let's say mu of AT, mu lambda of AT, so you should get something like this, and that is an equality. So that is an equality, okay, with the LHS, and this is an upper bound, so that's the significant difference in there. Exactly. And once we go to the TV, since we can tensorize or decompose it, we can get it down to the lower bound. Okay. But again, I'm skipping the rigorous part of it, but these are the main intuitions that give rise to the TV. Okay. So the whole idea is like using the, so this is called the group privacy property of differential privacy, and the KL is just rewriting of it, and this is the use of the maximum coupling between them. Okay, the coupling that kind of made them the most close together basically. So this is the most indistinguishable coupling you have in hand. So these are the two main key things. Rest you have to do rigorously with the proper measure and stuff.
What are you assuming about the distributions here? About the distributions? P and P prime?
Nothing. So this is purely generic. You don't have to go for exponential family, nothing. Just you should be able to define the measure properly. That's all. Yeah, yeah. Basically, very similar to the Latimore's book, the canonical measure. If you can define it, everything is good. Okay. But for BI, obviously, naturally, we need the first moment to be finite and defined. Yes. Yeah, and also here because the K-length needs the first moment to be finite and defined. Yeah, that's the only restriction. Anything else? Okay. So from this we understand that we address this question. So when we started this, we said that what is the information theoretic quantity that we want to control that dictates the differentially private bandit scenarios, and we see like across utilities, across models, what starts to dictate this is basically there's a one term dependent on KL, another term dependent on total variation and the privacy budget itself, right? So these two things kind of play against each other to define how your problem is hard or easy. Now the question is, okay, got a universal technique to design lower bounds. Can we design a universal technique to derive algorithms which are as optimal as possible? And also we don't want to go and tell people, you know, like design bandit algorithms from the scratch. You have to use like existing algorithms, but as optimally tune them as possible. So we start to get a very interesting generic wrapper. The wrapper has three things. One is forgetting, one is adaptive episode, and another one is noisy indices. Noise part I have already told you, because a statistics calculation, which is an average of observation, is a deterministic thing, right? So you have to add some noise to make it randomize and satisfy differential privacy. So you have to add some noise. Okay, we agree on that. But then if you want to achieve good utility, you don't want to add too much of noise. So that's where these next two terms will come into play, the forgetting and the adaptive episode. So let's look into the generic recipe. So we are working with this table, right? At any point of time small t, what I do typically in any bandit algorithm, try to calculate a sufficient statistics from the sequence of observations generated from this table. And then I want to add noise to it because I want to obfuscate this deterministic procedure. So I use the noisy statistics to choose the next term, right? That's typically what we are talking about. So the first question that we have to answer is characterize the sequence of sufficient statistics. That is the sequence that is enough, that gives you enough information to choose the next term optimally. Okay, so that is the first thing. Second is this estimate this sequence of sufficient statistics privately. So how much noise to add, how much minimal noise to add to calibrate and achieve the differential privacy. And then you want to run the algorithm in phases, because if you keep on adding this noise at every point of time, the effect of that will come up in your algorithm at every point of time. And this noise will be aggregated throughout your algorithm, right? So in the end, your private statistics will be whatever aggregation you have done plus capital T number of times you have added noise. So basically your added noise will blow up with capital T, and since it is a noise that depends on epsilon, is constant on epsilon, you can never achieve anything sublinear on T, right? So what you want to do is add as low number of times the noise as possible. So this is why we run the algorithm into phases and we try to forget the previous steps. And then the finally is like, okay, calibrate and add noise. That part is fine. So let's take an example. So this is one of the popular algorithm that you study in your bandit class, one of the first algorithms, that is the upper confidence bound or UCB type algorithm. So what this family of algorithm does, from philosophy point of view, this does the optimism in the face of uncertainty. What it tries to do, it tries to calculate the average reward, which is the sufficient statistics, because you are trying to get the arm that has the highest average reward, right? So the average reward you have, empirical average reward you have at hand is a good proxy of this, right? Now that is not enough. You have to be statistically sure that this is a good representative for choosing your optimal arm, or good representative of the true reward of this arm. So what you start to do, you add a confidence bound to it, because you can prove statistically that your true reward is far from this average observed reward by maximum this amount. And what is that? That is roughly the square root of 2 log t divided by number of selections of this arm till time t. So this is an example of an index that we can use for our bandit algorithm, and then if we have such index for each of the arm, we choose the arm with the highest index, right? So this is a classic bandit algorithm. Then you might want to use the variance and get something more tighter called UCV, where you don't know the noise variance. And here implicitly you are saying you know the noise variance, and that is 1. Okay. So these are the things you can improve on. I will not go into that, because our main point is how to have an epsilon differentially private version of it. So the whole point is, now I want to create an index on this sufficient statistics that is epsilon differentially private, and I want to calculate this noisy index, because I have to do noise addition as minimum number of time as possible. So the idea is, if I think of this interactive procedure, so first I pull each of the arm once, R1 and R2 is the observation. Then I pull the third arm, the first arm one more time, or one of them using the algorithm. And then I pull this arm twice of that. And then now I pull this arm like 1 time, but since I pull this first arm 2 times, I'll pull it 4 times, and so on and on, right? So basically I'll start to double the number of times I pull each arm. So it is kind of doubling the arm dependent doubling of each episode. So basically you are trying to say that more and more I get sure about each arm, I can keep on playing, I can keep on being greedy on that without updating the statistics. And then when I calculate the mean at this point of time, I use only these 2 rewards. When I calculate the mean at this point of time, I use only these 4 rewards. I forget everything that has happened in the history. Okay, so what I am trying to do is, first I am trying to induce a phase where as if each arm's observations are independent of each other. Why this independence? Because if I want to ensure differential privacy on a dependent data, I have to take care of this whole sum, right? So my calibration will depend on the number of data points I have directly. It will grow with that. So what I want to do, I don't want them to grow too much, so I am kind of doubling them. So rather than taking 10 data points at this point to add a noise, I'm just considering 4. So this decreases the amount of noise I add. Along with this kind of allows us to calibrate or add noise at minimum number of times. So if you observe this, by the time you reach 12, you have done maximum 1, 2, 3, 4, and 5 noise additions, right? And you can show that if you go through this procedure, after capital T number of interactions, you have never had to add noise more than log T number of times, because it is doubling, right? So you have to do maximum log T number of noise addition. And then for each of the phases, you add a calibrated Laplace noise to compute the indices. So now, if we go more concrete and look into the index of the ADAP UCB, you see that this was, so you now have defined phases or episodes. So let us consider this is the episode L. So this is the empirical average reward that you have seen till episode L. This is the classic UCB bonus, but now truncated at episode L, right? And then you add a Laplace noise to it. And the Laplace noise depends on what? It depends on this epsilon that is chosen and 1 divided by the number of selections of this till episode L. This is under the assumption that each reward is bounded, which I have forgot to write, but okay, oh no, I have written it. Yeah, for rewards bounded between 0 and 1, we can ensure privacy in this way, because you can show that if one data point changes in here, right? Since it is average of this number of selections of arm A till episode L, number of things, so it can change maximum by 1 divided by this, right? So that's why you add a noise that has a variance 2 divided by epsilon times this thing. Okay, so this in differential privacy is often called sensitivity. If this is not clear, so let us take maybe one simple example. If for the people who have not seen differential privacy before, is that so if you have a database D and a neighboring database D prime, and if we apply a function f on top of this and f on top of this, sensitivity is the maximum amount this fd and fd prime can differ. And for average, this differs. So if we take, then this difference, the delta, is maximum 1 by n. Okay. So that's why you have calibration, this 1 by the number of selections of arm A till time t. Okay. So that's why you calibrate it like this. And now you have to take care of the confidence interval for the noise addition. And if you do it for Laplace, you can see this is exactly 2 divided by this, log t divided by this quantity. Because you have till now can possibly add log TL number of noises only. Okay. So this is just a union bound, you can think of it. And that gives you the algorithm with tight possible, the exact information theoretic quantity you wanted in the end. Okay, there are some alpha factor issues, and which was annoying to us that we cannot take alpha to exactly 1, but we had to have a alpha greater than 3. And still we see like this algorithm, if you run it, exactly it starts to show the property that there is a high privacy and a low privacy regime. In the low privacy regime, it is independent of epsilon. And obviously with respect to existing algorithm, it works better. And if you do the same again in the base term identification scenario, you can get an algorithm that actually achieves this T star KL and T star TV exactly. There are some constants which were off, but later on we have been able to remove it, luckily. Yeah.
In this setup, do you need to change the batching procedure or it's
No, same. So just basically this selection procedure. So here basically, okay, yeah. So here when we are doing the selection, it is a UCB mechanism. There we use a tracking or like the top 2 mechanisms as we. Okay. Yeah, I have backup slides in there. I can maybe present later. Okay. So this says that this mechanism is quite general and quite optimal way of turning any usual bandit algorithm into its optimal differentially private counterpart. Yes. Yes.
how does that, like, you do geometric patching for each arm?
Yes.
Yeah, you could have injected noise at log t, like at time 1, time 2, time 4, instead of looking at doubling the number of pulls for a particular arm and
Yes.
right? That's another batching.
Yes.
Do. How does that compare with this? Do you know?
So in those cases, you can show in worst case, like there are certain environments where you have to incur higher regret basically. So this arm dependent batching, so basically, okay, here you are saying that, okay, if we go without arm dependent batching, right? So you apply this. So in those cases, you cannot control exactly the number of times you pull each arm. So that creates a randomness in the analysis of this Laplacian itself, and also the randomness in the confidence interval. And it becomes hard that how now you can design a martingale all on this random variable itself, right? And then you have to pay another bonus for that. So we didn't want to go into all that complexity, so we did arm dependent. Yeah. Okay, so if we are, so okay, any question further? Then we are good to go. Okay, so now what we have understood or studied today. So privacy definitions in the bandits. So given a trusted centralized agent, table DP emerges as the privacy definition that we want to follow and use in all other setups. So even if you go to contextual bandits or more general setup, we stayed in the simplest finite armed stochastic bandit setup here. If you want to go the more complex realistic ones, still this is the definition that you should follow and you can work on. The hardness of the lower bounds are super interesting because, at least in my experience, this is the first time I saw total variation or TV appearing in any hypothesis testing or like bandit problems. So that gives rise to like whether we can design much better and tighter algorithms, because what I have shown you is a kind of a reduction to like Bernoulli's or exponential families basically. But this lower bound is not dependent on exponential family or anything. So that says also even in private hypothesis testing, can we do the same? And then the next question is like, obviously we can design generic algorithm with these three techniques of adaptive arm dependent episode, forgetting, and then calibrated noise addition. And that works across utility objectives. But what we didn't know back in time until 2024 is that the regret lower bound indicate two regimes of hardness with a very discrete cut, right? So there's privacy and then there's no impact of privacy. But that's very unusual, like that's not how most of the natural things work, right? There must be a continuum complexity that should appear and that should be changing with epsilon continuously. And then the other question is like, at least due to this alpha greater than 3, the upper bound is 4 times higher than the non-private bound. Can we reduce this gap? Because when we are doing the analysis, we saw it's completely mechanical and limitation of our analysis. This should not happen basically. So in 2025, like we have been a very recent work, we have been able to address this. So we have been able to remove this too. I'll probably answer that first because yeah, this is the slide I included because Shubhada asked me to. So then what happens in there that we see now a new divergence appearing in the lower bound. And this is not anymore the minimum between the total variation or the k-length. This is a completely new phenomena where you are trying to interpolate between the total variation and the KL divergence. So what you see now, if one of your environment was X, so you are calculating the total variation distance from X to another distribution Z, and then you are calculating the KL between Z and the confusing instance you have at hand, that is Y. And what is this Z? Z is an intermediate distribution between X and Y. So what you are trying to do, you are kind of interpolating at the same time the complexity of differential privacy and the complexity of partial information. And you can show that this quantity is strictly less than equal to the minimum of total variation and KL between X and Y. So this is a quantity. So previously we had this type of structure that where you go like this, and this is the epsilon where the phase, let's say the phase change happen. And now you are saying that you have actually a tighter lower bound which goes roughly like this and then merges there. Okay, so this is kind of a smooth transition between them, and you know this transition phase much more clearly, and you start to understand where the KL appears, and you see this is very clear, a problem dependent transition that you can compute for every environment. So this is something super interesting, exciting. After all these years, like this is the third time probably I proved the lower bound, and every time I said what I have proved before is wrong. So that's very nice. So we didn't expect this to be this rich problem, but now the challenge is every existing series of work I have presented to you should be revisited, should be made tighter, And yeah, this is quite an open problem. So recently Ashraf and Mark, like two of the students they have been shown that this also in a fixed confidence BAI, but yeah, in other settings we don't know. And for the tight upper bound, we have it only for Bernoulli's, nothing else. So this is kind of a very wide open scenario. Yeah, so that's all from my side, and this is a part of the research I like to do, that is developing theory for robust, private, fair, and explainable reinforcement learning. And we have talked about just one axis of that, that is how to trade off this privacy and efficiency here together. So thanks for listening, and any question? Yeah.
Let's all thank the speaker. Thank you very much, Professor, for a wonderful talk. So let's take questions.
How hard it is if I go from epsilon to epsilon delta?
That's a good question. So this trick is the main bottleneck in there. So here, when we are doing the maximum coupling for this part for epsilon, then we can really say this is epsilon times TV. But group privacy, so even the problem starts much before. The group privacy property goes crazy if we start to go for epsilon delta. And how it goes crazy? Like it starts to appear like delta d ham, right? And that's really a bad news, right? Because in this capital T number of steps with this k number of entries, it can go really linear on T and K, and that's really bad. So then to prove, we have to go for a good definition of differential privacy, approximate differential privacy. So what we have done in our paper, this one in 2024, like this one in 2024, we started to look into this zero concentrated differential privacy. Why? And what is the definition? Because we have seen that in the end we want to control the scale, right? So if we want to control this scale, we don't need such an absolute worst case definition. Maybe we can go for such a definition where your scale of MD and MD prime is bounded by some factor times the d ham, right? So this is kind of the definition you know that appears in rho Z concentrated DP, as they call it. And this is true if you add a Gaussian noise with certain calibration, you can achieve this basically. So that makes sense, that is realistic to apply, and you have a good differential privacy property. Then appears one more problem. Now you are working with this, sorry, no, that was a bad notation. Kl rho d ham square, okay, that appears. Now this square is the source of all problems in your life. So what you start to see that now if you try to write the stochastic version, this is like rho TV plus rho times TV 1 minus TV. Sorry, rho TV square, rho TV times 1 minus TV, something like this start to appear. Again, I am not writing rigorously, but it tries to say that basically you start to see the variance appearing. So rather than this direct TV distance, the variance start to appear in there. And then what we can do is we can obfuscate this term and get problem independent bounds which match the orders. So we can have upper, lower bounds, everything matching the orders. But if you really want to go problem dependent, as we have done with the KL-inf and the TV-inf, this is an open problem. And this is what kind of we mentioned a bit briefly in our open problem in Colt. And also there's one more open problem in there. This is interesting if and only if you want to add Gaussian noise. Because with Laplace noise, all this perfect, right? Everything works. Because Laplace noise satisfies epsilon differential privacy. But with Gaussian noise, we have to go for these approximate definitions. And they are needed realistically in linear bandits, linear contextual bandits. And in those cases, again, the other open question is what is the tightest lower and upper bound? And that's again still not solved completely. There's been a recent by Alexander Raftelin's group, like who solved up one of the open problems in there, but there are still multiple open in this setting. So you might have a look, or we can discuss that.
One more question, I didn't understand, why are you forgetting?
Okay, so let's go back here. Okay, so here as you see that this depends on 1 divided by the number of selections of A till episode L, right? So here you know that, so here you know that the noise variance depends on these 4 things, right? But if you had to add noise on an aggregate of all these things, this would depend on the 10 data points. So you are more sensitive in that case, right? So you don't want to be that. Oh, and one more, sorry. One more thing I missed. Maybe I should have talked about that here because you are probably interested in the privacy part of it. This allows us to use something in privacy called this parallel composition. You can have a look, because the cool part is if we create such episodes and forget anything before, already since I have added noise in the previous case, I have made anything private for the previous user. So now what I'm caring about is the user that appears only in that episode, and that creates my differential privacy. I don't have to do a composition. It is just parallelly, at this episode I have seen you, I made you private, then I forgot you. In the next episode, I made the next people private, I forget them. But if I keep on using the whole thing, I have to do adaptive composition, right? And the epsilon will increase with the square root of log t. So we don't want that. Yeah.
Thank you.
Thank you. Yeah, good questions. Thank you. Okay.
Any more questions? I hope Professor has answered all your questions. If you still have more queries or want to connect with Professor, please feel free to do so by having some refreshments at our coffee hut. Thank you all and have a great evening.
Thank you. Yeah, thanks for organizing. Thanks.